Hello, welcome back to our subject. Okay, so we will now proceed with your module 6. This is now about beam deflections. Okay, so we are just finished with your module 5, which is about the beam stresses. Okay, so in this module 6, we will be discussing your deflections. Okay, deflections of beams. And then in this unit, in this video, we will be discussing about the double integration method. Okay, one method for us to establish deflections of beams. So in this unit, we are going to, these are your unit learning outcomes. We are going to write singularity equations. Okay, what is the singularity equation? And then how will that differ with the moment equation that we used to establish before in the previous module? Okay, and then of course to solve beam deflections using the double integration method. So okay, if you will try to recall, as I've mentioned before on the previous modules, that using your moment diagram you can actually predict the shape of the deflection or the deformed shape of the beam. And of course, the deflections there is actually the what do you call this one? The distance, okay, of the original orientation of the beam to the deformed shape of the beam at a certain location. So let's say you want to get the deflection at this distance x of your beam given on top, then that is the vertical displacement. Okay, we call that one also as displacement, vertical displacement from the original location or the original orientation of the beam to the final, which is this one. This is your final. So that vertical distance is what we call as the deflection. So at other distance, let's say another distance x, okay, there will be a different deflection y. Okay, so actually that y or that deflection y could be expressed in terms of a distance x or a coordinate x reckoned from the leftmost or rightmost. But of course, since we are used in moving from left to right, we will reckon the distance x to the leftmost part of the beam. Okay, so now if you can express the shear and then the moment of the beam, internal shear and internal moment of the beam with respect to the distance x, we can also do that in your deflection. We can express the deflection in terms of distance x. So actually, since we are getting this equation of y as a function of x also from your moment equations. Okay, so that's why we can express this one. So that all we need to do now, if you have your equation y in terms of x, all you need to do is substitute the distance you want to establish or you want to investigate the deflection to your equation of y, a function of x, then you will end up with a value of y, which is your deflection. Okay, so that's it. We call this one elastic curve. Okay, we call the deformed shape, okay, of the beam as the elastic curve. You can read about the description here. Okay, you can read about the description here. Okay, you can further read that one. So by the way, how is this relative or how is this important to the actual applications on beams? Okay, how is that deflection important? Okay, if we are on design of structures, okay, of designing of beams, it is not just necessary for us or it is not just important for us to design the beam for that beam to resist the given loading, okay, or for that to pass or for that to be able to carry the loading. That is not just enough. We have what we call as the what do we call this one? We have what we call as the serviceability of the beam. See, serviceability, that beam should be carrying the load intended for that beam. At the same time, that should maintain a good posture, okay, or that should be comfort, so that if ever this beam is, let's say, carrying a slab and the slab is of course for the crowd, then the crowd which is within the top of the beam will be having comfort, will be comfortable, okay, since of course because of the limited deflection of the beam. Or again, let's just imagine that you are the one or you are one of the crowd on top of the beam, and the beam, it is obvious that that deflected a very big amount of deflection. So what can you see? That will be big sag on the beam, and then that will make you uncomfortable because of course especially those individual with no knowledge about technical knowledge, then they might be worried about the big deflections of the beam. Or of course, that also might because due to the movement of live load, there will be, because of this big deflection, there will be a big vibration, vertical vibration, and that will cause, of course, uncomfortability also within the crowd, which is utilizing the facility. So it is that important for us to what we call this one, establish or to analyze or to investigate also deflections, not just the capacity of the beam, but we need also to investigate the deflections, okay, for serviceability. So the most of the time, okay, in many building codes, the maximum allowable deflection of a beam is for that not to exceed the 1/300 portion of or a ratio 1/300 of the entire length. So let's say your length there is 8 meters. Multiply that one by 1/300, and then that is the allowable, okay, the maximum allowable deflection by most of the building codes. But of course, there are a lot of factors to consider, okay, so that is not fixed. But that is the most maximum allowable deflection of most of the building codes. Okay, so we will now proceed with your double integration method. Okay, how will that be? How will we establish the equation of y in terms of x? Okay, by integrating, or how will that be applicable by integration, or how will that be established by integration? Okay, so if we will try to recall the derivations that we had before, okay, when we discuss your stresses in beams, we derived a relationship of the moment, okay, of the moment within the beam to be equal to your EI over rho, or over P, okay, over rho, or this is read as P, or that is rho in a Greek letter. So again, your E there, so your moment actually within your beam at a certain cross section is a function of the strength. E is your Young's modulus, that is the strength with respect to the type of material used, and then the I is your moment of inertia, that is the strength with respect to the section, okay, to the shape of the section, or the orientation of the section itself. And then of course there your rho there is actually has something to do with the curvature, okay, so actually we call that one the radius of curvature, okay. So that moment, we derived this one before in your previous module, that the moment is equivalent or equal to the Young's modulus times the inertia all over the radius of curvature, okay, we derived this one before. So therefore, for now, we will be concerned with those beams for which E and I are constant along the entire length of the beam. Okay, so for this discussion, we will try to focus, or we will try to limit ourselves into E and I to be constant. Okay, what does that mean? If E is constant, the entire type of material used is the same all throughout the beam, which is of course the common. Okay, seldom that we will be having different types here, unless that is a what we call this one is a composite beam. Okay, so unless this is a composite beam, then E will be constant. So that is a single type of material, and we will try to limit, of course, our discussion also within I to be constant. If you say I, that is the moment of inertia, and that is actually with respect to the cross section. So if I is constant, that means this beam has a cross section of constant all throughout its length. Okay, so let's try to limit our discussion in that E and I to be constant. Okay, so therefore, at any certain type of loading, this is a variable loading, then you will have there, of course, a variable moment, and of course that is with respect to different distance. So you will have a variable m, and of course rho. It depends. That depends on the curvature. So we will only end up with m and p as a function of distance x, since we will try to establish an equation of the deflection y with respect to its ordinate or distance x from the leftmost part of the beam. Okay, so the y, okay, in this discussion we will be establishing that y is taken to be positive in upward direction. So if that beam is deflected upwards, Then at that certain cross section wherein the displacement from the original beam orientation to the final beam orientation or the formed beam shape, then if that is on top, that will be y positive, or if that is now below, therefore that is y negative, or deflection is negative. Okay. Then if you will try to recall from your differential calculus, we have this what we call as the curvature. If you see curvature, that is degree of the degree of the sharpness, or that is the sharpness of the curve. Okay, and that is actually the inverse of the radius of curvature. So if we say radius of curvature is that rho or p, then the curvature itself is the reverse or inverse of that is 1 over rho or 1 over p. And that curvature, which is derived from your differential calculus, is equivalent to the second derivative of y with respect to x all over the quantity 1 plus the square of your first derivative, the quantity raised to 3 halves. Okay, so this is derived from your differential calculus. You can go back and check that one. So this is your curvature. So instead of, so if you will try to substitute this one to your equation, which is derived here, you can say that m is equal to ei over that value of 1 over rho, or the curvature. However, for simplicity, since that term here, which is the slope, and then most of the time the deflection, since that is actually in millimeters, okay, the deflection, if that is within a length of meters, deflection expected there is just a very small number, which is could be expressed in millimeters. Okay, which could be expressed in millimeters. So we will be expecting that the slope, okay, by the way, look at this, your dy dx, that is the first derivative, and that is corresponding to slope, isn't it? The slope of the curve within your x and y axis. So imagine that one, that the curvature is very big, wherein the slope of any point within this curve is small. Okay, since of course the deflections are small, so that the slope here is a very small number, and then we are going to square that one. Okay, a very small number, and then you are going to multiply it again to itself, will become a lot smaller than the original value. So that compared to 1 will be negligible, so we can actually consider that one as 0. Then that will be left to 1 raised to 3 halves, so that will remain 1. And then we can now simplify this right side of the equation, which is the curvature, could be simplified as approximately the second derivative of y with respect to x. Okay, so this will be simplified to 1 due to squaring your slope, which will be almost 0. So if that is now the approximate value of our curvature, then we can simplify the m is equal to ei over rho to be m is equal to ei times that equivalent of 1 over rho, or the curvature, or that is the second derivative of y with respect to x. Or we can write that one as the y double prime. Again, prime stands for derivative, so double prime is means second derivative. Okay, so now you can say, you can now simplify our equation into moment within the beam is equal to Young's modulus times the moment of inertia times the second derivative of the equation of x. Okay, equation of x that we will be establishing out from your beam. Okay, orientation of the beam. So that's it. That is this is what we call now as the Euler-Bernoulli equation. Okay, this is what we call the Euler-Bernoulli equation, wherein your m there, you can now establish that one from your moment equation. Okay, we can establish that m from the moment equation, just like what we did before, and then equate that one with your ei times the y double prime. Then what are we after here is the deflection, which is y. So for us to get the y from your y double prime is we will be integrating it twice. Okay, for us to bring out the y, which is the deflection. However, as you recall, okay, so this is what happened. Okay, so again, your m there will be a function of x. Integrate it once, you will have this y prime. Your y double prime will become y prime, and you will be having what we call as the constant of integration. Okay, and then since of course this is not a definite integral, so we will not be having a limit. So you will be having what we call as the constant of integration. Let's call it as c1. However, we are not yet done, because that is just the slope equation. From moment equation, we will integrate, that will be slope equation. and then integrate again before we will bring out the y, which is the deflection equation. So we have a c1, integrate this one again, you will have another c, which is another constant of integration. So you will end up with an equation of x and c1 times x and then another c2 in your equation. And then these values of c1 and c2, we will establish that one by substituting the boundaries, okay, the boundary values in your equations. Wherein we know that at a certain support, okay, the deflection should be 0 because that is of course supported. So using these boundary values, we will substitute in this deflection equation, then we can establish the values of c1 and c2 in terms of a value or a constant. Then you will end up this right side to be purely equations of x, and then you will have this ei. So if you are given the e and I of the section or the beam, you can cross multiply that one as a constant, then you will have the y, which is a deflection in terms of x only. However, okay, if you will try to recall the moment equation, we established that one. Okay, by the way, these are just additional explanation which I just explained briefly. Okay, so you can read about that. However, what I'm trying to pinpoint here is that your m equations are established based on each of the chains of loading. Okay, or we can divide that one by what we call this one segments. In this segment, the type of loading is constant. In that segment, that type of loading is constant. So we are establishing the moment equation on each of the segment. So how are we going to express that one in a single equation? Since of course, if we are just going to integrate one equation, for that to represent a value of y or a function of y in terms of x, a single equation for the entire beam. So how are we going to combine all these segments equation, moment equation of each of the segment into a single equation for the entire beam? We call this one the singularity equation. So how are we going to write this one? Okay. So that is the slight difference from the moment equation we established before. Okay. So how are we going to do that? Is we are going to the same thing, cut section or the segment, get the moment in terms of x, cut the second segment, but this time we are going to put this one into a single equation. However, there is this limitation of this equation wherein if we will establish there an equation of x minus constant, okay, just like what we had before, x minus a number due to the distance of the segment, okay. However, there is this limitation, so we will be using what we call as the pointed bracket. Instead of the parentheses, we will be using a pointed bracket uh, because that will be restricting the value within this bracket, okay. So that will have a certain value with respect to the values of x relative to a. So for example, okay, for example, this bracket or the pointed bracket is including an x minus a, and the x there or the value of that, if you will if you are going to what we call simplify this one, will be a negative, or that is a less than 0. So the value of the bracket inside is less than 0 or the negative value, then we can just make this one 0. Okay, we will not include the negative number, rather we will just make that one 0. Or simply that will happen because your x is bigger than a, so that you will end up with a negative number here. So if the value within the bracket is a negative, or the x we are substituting is bigger than a, then we can neglect that one, we can just make that one 0. We will not include that one in our moment equation. Okay. However, if it is the other way around, wherein the x now is bigger than a, so you will end up of the value inside the pointed bracket to be a positive number, or that is 0, then we can you can include that one in the equation, or we should include that one in the equation. Okay, so that is the difference of your singularity equation with your simple moment equation of each segment. Okay, so moment equation of each segment, combine that one into a single equation, we call this one singularity. But instead of using a parenthesis, we will be using a bracket. Again, a bracket stands for restriction, wherein if x is bigger, or if x is smaller, sorry, a while ago I am mistaken. If x is smaller than a, that means that will be giving us a negative. Then the entire term will be considered 0. But if that is a positive or 0, then we should include that one in our moment equation. So, okay, again, that is just the explanation of this. Then, of course, later on, you will now end up with an equation which is an x function of a, or a y function of x, I mean, and then you will have there a parenthesis which is in terms of x, and then that is raised to n. Then if you are integrating this one, this is just power formula. However, again, we need to satisfy the restriction of your singularity equation, wherein if x there is smaller than a, then that will be a negative number. Then we can forget about that term. Okay, we can get rid of that term from your entire equation. Okay, so we will be having example for us to establish that one. Okay, so let's have an example. Okay, so consider the given beam and determine the deflection at D, which is x equals 3. So that is, of course, since we are reckoning our x from the leftmost, which is from point A, then we want to get the deflection at exactly point D. So that is just your x equals 3 from A. Okay, consider EI to be constant. Okay, so we will just consider EI to be constant, but once that is given, all we need to do is substitute. Okay, so first and foremost, of course, we will solve first the reaction. So take a moment at E, you will get the reaction at A. Take a moment here, you will get the reaction at E. So you will have this as 13, and then you will have that as 17. So now, your moment equation. So, okay, so this is the difference of the simple moment equations which we get from each segment with your singularity equation. So singularity equation, we will combine that one and we will be using the pointed bracket. Okay, so if I will to cut somewhere here, okay, you will be having the moment of this to be clockwise, and then that is multiplied to the distance x, of course, since that is a variable x. And then I will go here, that will be added. Okay, so as you can see, before we are taking it per segment, so moment here is different from the moment equation here, or separated, but this time we will combine. Okay, so take a moment here that is included to be clockwise, 17 times x, and then I will now move here, that will be included, and that will be a counterclockwise to 10 times the moment arm, which is x minus 1. Okay, and then move, that will be added, which is a counterclockwise again, negative 5 times the moment arm, x minus 2, and then somewhere here, so that everything will be included, will be 15 negative, and then x minus 3. So this is your moment equation, and just all you need to do is equate that one to EI y double prime, and then of course we will integrate this one twice. So first integral will have the slope equation, second integral will have the deflection equation, but of course do not forget your constant of integration, C. Okay, so integrate this one. This is just simple as power formula. Okay, so n plus 1 is x raised to n plus 1 over n plus 1. Okay, so that is simple power formula. So that will become squared, and then you will have this 2 below, and then of course this will be your quantity, and then that is just simple. Okay, power formula again. So this quantity raised to 2 all over 2. This quantity raised to 2 all over 2. This quantity raised to 2 all over 2. Do not forget your constant. Let's say that is C1. And then that is your slope. So we need to integrate it one more time so that you will end up with y. Okay, by the way, EI is constant, so you can forget about that while integrating. So we will focus on the variable y and x. So integrating your y prime will become y, so that is now your deflection. So integrating again this side, okay, power formula, n plus 1 will be 3, multiply the 3 below, that will make it 6. 3, multiply again, that will 6, be 6, that will be 3, multiply 6, 3, multiply 6. And then do not forget integrating a constant that will add x to it. And then do not forget to add another constant, since again we did one more integration. Okay, we did one more integration. So this is your equation of deflection. So if you want, all you need to do is cross multiply EI in this complicated part here, then you will have the equation of your deflection with respect to the distance x. However, again, do not forget the purpose of your pointed bracket. Okay, we need to screen the terms due to that pointed bracket. So again, the pointed bracket, the inside of that should always be positive. If that will be a negative, then we can forget about the entire, or we can just make that one 0 so that it will make your entire term 0. Okay. So that, again, that is the restriction of your pointed bracket. However, before doing that, we need to know the constants C1 and C2, because later on that should be only in terms of x. So now this is where we will be substituting these, what we call as the boundary values, or if you will try to look here, we are getting a deflection, and that is supported at A and supported at E. So we should know that even under the loading, that should always be its original location, so that there is no deflection at the supported points. So A and E, Y should be 0. So at x equals 0, that is at A, since again x is the distance horizontally from the leftmost. So at that very first point, that is x equals 0, y is also 0. So substituting x0, y0 in your equation here, everything will be 0. This will be 0 because of that y. This will be 0. That is not 0, but actually if you substitute 0, your pointed bracket, the inside value is negative, so make it 0. That is also negative, make it 0. That is also negative, make it 0. And then that is 0, so C1 is cancelled, so you are left with C2 is equal to entirely 0. So therefore C2 is 0. By the way, that is Kn times meter cubed. Why is that? Okay. Your moment equation, you are expecting kilonewton meter, since our unit here is kilonewton meter. However, we integrated. So again, integration is adding one more degree, isn't it? And then the degree that we are adding is a variable x, which is a distance. So recall, differential, we are reducing a degree. Integration, we are adding a degree. So if we integrated once and we integrated that in terms of x, so we added one more degree of x. What is x? That is a distance. So from moment, which is kilonewton meter, multiply another meter will be kilonewton meter squared. Multiply, and so your C1 is kilonewton meter squared. Multiply again another x or meter will be kilonewton meter cubed. So if that is squared multiplied by x, this will be kilonewton meter cubed. And then entirely your C2 should be automatically kilonewton meter cubed. Or the entire of this is kilonewton meter cubed, so that if we will divide it by E multiplied to I, multiply your kilonewton meter cube here, that will be simplified. Okay, cancellation of variable or units, you will end up with entirely meter, which is for our distance unit y. Okay, so again, so that is your kilonewton meter cubes, but that is 0, as I've said, substituting x0, y0 at your point A. And then we know now at your another point E, y is 0 also, but the x there is 2 plus 1 plus 1 plus 1, which is 5. So at x equals 5, y is still 0. Substitute that one. So y is 0. So this left side is 0. Left side will be 0. But that will be 5. This will be 5, 5, 5. Okay, now look at the pointed bracket again. Pointed bracket. Okay, this is positive. So we should include that one. Positive, so we should include. Positive, so we should include. So nothing is screened. So calculating this, and of course your C2 is 0, so you substitute there 0. Your unknown here is only C1, multiplied to your x, which is 5, then your C1 will be calculated as negative 41. So now substituting C2, C1 to our equation, working equation, you will have this C1 to be negative 41x and then plus 0, but of course do not need to add your C2, which is 0. So this is now our moment equation. I mean slope equation. Okay, this is now our slope equation. That is slope deflection equation. So now all we need to do is substitute the x which we are after, that is 3. So make your x equals 3. So if that is 3, 3, 3, 3, then okay, no problem with that. But this is a pointed bracket, that is a positive, so we are good. This is a positive, so we are good. That is 0, so it's okay. But this will be of course useless since that is 0. So of course 3. So calculate this one. Now that will be entirely simplified to this. Again, this is removed because that is 0, of course. So that will be simplified as EIY is equal to negative 182 over 3. So this will be entirely negative 182 over 3, which is again kilonewton meter cubed. But if you want to solve your y, since that is what we are after, cross multiply the value ei below, and then if this is a given value, all you need to do is substitute, and then of course cancellation of unit, you will end up here with a value in meters, which is the deflection at your point D, and that is a negative even if you will substitute ei. Ei are just constants. So if that is negative, the entire y will still be a negative, so it means that is below. So therefore, we are correct for assuming that this is to bend that way. Okay, that is a negative deflection. So again, if you are given ei, just substitute the values of ei, but of course be careful with the units. We derive this one from kilonewton in meter, so that is kilonewton meter cube. So you should maybe transfer this one into Newton millimeter and then substitute that in terms of Newton millimeter, or do the other way around. Okay, so that is just playing around with the units. Okay, so let's have one more example. Okay, so this is your number 2. So consider the beam and determine deflection halfway between the supports. So if we say halfway, that is at the distance. Okay, so 14 plus 2 is 16 divided by 2 will be 8 plus, of course, 2, since we are getting the distance x from A. So at x equals 10. So now first of all, we need to get the support reaction. So take a moment here, you will get the 187.5. Take a moment here, you will get 3312.5 newtons. And then of course, by the way, drawing your moment diagram, you can predict the shape of your elastic curve or the deformed shape of the beam. But of course, we do not actually need this one. We can predict that one by the sign of your y. Okay, we can say if that is on top or below by the sign of y. Okay, however, but if you want to have the complete elastic curve, then you need to draw your moment diagram, and that will reflect again. So that is discussed before. So moment equation, singularity. Okay, the singularity equation or moment equations. Equate that one with your ei y double prime. So establish your moment equation, singularity equation. Okay, so cut here. So moment there is clockwise 4,000. So we do not need the moment arm since that is a moment. And then if we will move, okay, surpassing your 187, that will be a clockwise. So plus, and the moment arm of that is x minus 2. And then move here, it will be including this, but that is now counterclockwise. So 3,5, okay. And then the moment arm is x minus 14 plus 2 will be 16. So x minus 16. So now integrate this one once, you will have the slope equation. So what that will be y prime, and then this will be 4,000x. That will be raised to 2 over 2, raised to 2 over 2 plus c1. Integrate it again, that will be your slope now, and then x squared over 2 cube, and then that will be 3 times 2 is 6 cube, 3 times 2 is 6. There will be x with c1 and then another c2. Okay, so now substitute our boundary values, which is at joint B or at point B and point D. We know that these deflections are 0 there. So at x equals 2, that is 0. So substitute, you will have here to be simplified, but this one, this is a pointed bracket. Of course, we need to screen this one. So 2 minus 2, so 0. So it's okay, but that will be making this useless. But this is a smaller than that, so that is a negative. So we need to scratch this one also, screen this one. Therefore, we are left with this and this one, and then C2. So we cannot solve C1 or C2, but we ended up with one equation. So I need to have one more equation to solve for C1, C2 since there are two unknowns. Okay, so substituting the second boundary value, which is at x equals 18, that is your point D. Okay, 2 plus 14 plus 2 is 18. That y or deflection is 0. So make your x 18. You will have this one. Okay, substitute 18, 18, 18. You will have now, you need to screen, of course, positive, so no problem. Positive, so no problem. So now you can simplify this into another equation of C1 and C2, which is 18 plus C1, 18 C1 plus C2 times negative of this combination of all of that. You will have equation 2. So from equation 1, equation 2, we can now calculate C1, C2, and these are the values. So substituting it back to your equation, your C1 is this and C2 is this. So now we want to investigate at x equals 10. Again, that is midway your point D and point B. Okay, so now substitute that x equals 10. You will have this as 10, 10, 10, and then of course 10. and then this is positive, yes, no problem, that is a negative. Okay, so 10 minus 16 is a negative, therefore we need to get rid of this. So we are left with this one, this to be 8, and then this is of course that one, and so this. So calculating this, you will end up with a negative 535,000 over 3 Newton, since we established that from Newton and meter. So Newton meter cubed, and then all over EI. So if you have your EI, substitute that one, of course apply unit cancellation, then you will end up with meter or millimeter. It's up to your conversion. That's the negative. So it means at x equals 10, so somewhere midway B and D, or that is midway B and D, that is your y. So it is a negative. Okay, it is a negative. Now, let's have one more. Okay, this will be our final example. So we had this before. So again, solve, but we want to get the deflection at the free end, which is x equals 30. So 10 times 3, so 30. This is your point under consideration. Okay, so get the reactions. Summate moment at A, you will have this 233.33, or that is 7,000 over 3 Newton. Take moment at this joint, then you will have that as negative. So going down 1,000 over 3, that is 333.33 Newton. And then of course establish again your moment equation, the singularity equation. Okay, so cut here, that is just a counterclockwise. So your reaction times x. And then cut here, you will now have the rectangular load. So now, this is important. Okay, how did we end up with this? That is just of course by ratio and proportion. So by ratio and proportion, let me just show you here. This is your beam. Okay, 1, 2, 3. The rectangular load is here. So these are your supports, these are your load, this is your loading. So of course, if I will try to cut somewhere here, for me to include this one, that is the distance x. Okay, that's the distance x. And I want to include this one, so I need to get the resultant of that, which is located at 1/3 from this base of the triangle. Okay, so that is the location of the concentrated resultant of this distributed load. So again, I need to get the value of this so that I will take the moment of that. And then of course, if that is 10, this is 10. And then this is x, then that is x minus 10. Okay, this distance here is x minus 10. So for me to convert that into a concentrated load, multiply or get the area of the triangle, so that is 1/2 base times height. But I need to know the height of this triangle in this portion. So how do I get that one? So given this x minus 10 as the distance, I can do ratio and proportion. So this is 10, that is 10, and that is given on that 200. Okay, that is, yes, 200 Newton meter. So by ratio and proportion, I need to get this one again for the area. So ratio and proportion, the let's say this is y1, let's say that is y1, is to the base, which is x minus 10, is equated to the big triangle. Okay, so the height is 200 is to 10. This is entirely 10, and that is 10, so 20. So actually that is reduced to 10. So your y1 is simply 10 times x minus 10. So cross multiply this one, that will be 10 times x minus 10. So that is the height here. So therefore the area is 1/2 times this times that. That is the area of this. But the moment arm, what is the moment arm of this? Okay, that is 1/3, since we are getting the moment from this base of the triangle. So that is 1/3 of the length. Okay, so 1/3 of that, so that is 1/3 of x minus 10. So going back here, that is our area here. Okay, 1/2 base, or this is the height, 10 times x minus 10, and then the base is x minus 10. So this is the area to be converted into a concentrated load. And then the moment arm is 1/2 of the base x minus, 1/3 of the base x minus 10. Then now, as we move on here, that will still be the triangle, so that's already there. This is just the additional, so that is now a positive, since that is a clockwise. I will use the entire value, 7,000 over 3, and then the moment arm is x minus 20. And then of course now, simplify, you can simplify this one. So that will be 5/3, and then that is x minus 10 raised to 3. Okay, So now I can make that one as our singularity equation. So make that one the pointed arrow, or I mean pointed bracket, so that we need to screen these values. But here no problem since that is this x, of course. Okay, so now integrate. Okay, sorry, this is supposedly y prime. Okay, so integrate one. So that will be y prime. This will be x squared over 2. Multiply that. That will be 6. That will be 4 times that one will be 12. That will be squared times that will be 6. And then you will have c1. Integrate again. That will be cube. 3 times 6 will be 18. That will be 5. 5 times 12 will be 60. And then that will be cube. 3 times 6 will be 18. And then c1x and then c2. And then substitute your boundary values. So at x equals 0, y is 0. So c2 is 0. So everything will be 0, 0, 0. This is 0, so that is a negative. So screen. Negative, so screen. So this is 0. So c1 is cancelled. So c2 will be 0. And then now substitute at x equals 20. Okay, that is your c. Okay, the deflection should be 0. So substitute, and then you will have the c2 to be 0, of course, so that it will be cancelled here, or we do not need to copy. Then you will be left here. Okay, this one is screen. I mean this is carried. Okay, so that is your 10, but this one is useless since that is 0. So none is screen, but this is useless since that is 0. Okay, so simplify, that will be c1 to this value negative. Okay, negative that value. And then now substitute your c1, c2. So your c1 is that negative value, and then c2 is 0. So you do not need to write that. And then now that is your deflection equation. So all we need to do now is substitute at x equals 30, which is your free end. So that is at x equals 30. Substitute values, and then okay, be careful again. These are your pointed brackets. So screen, is that positive? Yes, so carry. Is that positive? Yes, so carry. Okay, so no problem. Nothing is screened. But calculating all of this will be 1 negative 185.12500 over 9 negative. So again, it is below. And then that is Newton meter squared, since we established that from Newton and meter units. And then cross multiply EI. So if you have the EI, just substitute and then simplify. You will have the distance value of the deflection. Okay, so that is your deflection using double integration. So if you have any questions, just comment below the video, or we will discuss that one on the live meeting. So thank you very much for watching.